In this objective, we're going to be looking at 8.4 acid-base reactions and buffers. So the learning objective states that we should be able to explain the relationship among the concentrations of major species in a mixture of weak and strong acids and bases. So buffer systems are going to resist large changes in pH. And this is when small amounts of strong acid or base is added. So it will be consistent of two things that are in equilibrium with one another. So a buffer system is going to be stuff that is weak, and it's going to be two of them in equilibrium, because equilibrium means that you have stuff that's reactants and products that are going to be coexisting in that solution in this case. There are some buffer systems in our body and in many natural and man-made products, and this is going to assist with the maintenance of relatively constant pH levels. So our blood needs to have both H2CO3 and HCO3 minus present, and it doesn't have to be equal amounts, but the best type of buffering requires you to have a 1-to-1 ratio. But overall, these two components of the buffer are going to try to resist any changes in pH if something strong is being added, because if our pH of our blood drops honestly just a little bit below 7.35 or even just above 7.45, it will end up killing us. So it's very important for our blood to have a buffer, and a lot of other natural or man-made things to have buffers to help resist any of these pH changes. Now you have to realize when it comes to a buffer, it has to be something weak, because in this case, you'll be using up one of the components while making the other. But the issue is it can't consist of anything strong, because strong acids and bases are going to be dissociating 100%. Okay, so you don't really have any of the beginning of the acid or beginning of the strong base anyways. Okay, moving on. So like I said, a buffer may consist of only weak things. So let's talk about some examples. We have two. You can have a weak acid and its weak conjugate base. Some examples could be HF, the acid, and its conjugate base would be F minus. Or you can also think of acetic acid, HC2H3O2, and the acetate ion. Here, these would be examples of two weak things. One, whatever you have listed first will be either the weak acid or weak base, and then whatever listed second will be its conjugate. You can also write stuff like this if you want, but that's going to be for the next part, okay? So here, the other example is if you have a weak base and its weak conjugate acid. So I could rewrite this F minus and HF, okay? Another example is you can write NH3 and NH4, 1 positive. Here, NH3 ammonia is a common weak base that they use a lot in AP chemistry, so it's very important to get familiar with it now. And so if that's our weak base, NH3, if it gains that hydrogen, it will become ammonia. Let's move on to talking about diluting when it comes to a buffer system. If you actually dilute a buffer system with water, it will actually not change the pH. And that's because both components of the buffer are in the same container, so they're going to be actually diluted equally. So that ratio between them is not going to be changing. So we'll say that that ratio will remain constant, okay? We'll see some examples here in the other videos when we talk about the ratio between the weak acid and its conjugate, or the weak base and its conjugate. So there's actually 4 ways to make a buffer, and I've already talked about the first 2, but let's just rewrite them. So the first one is if you combine a weak acid, and you're assuming that this is just a solution of a weak acid. So I'm going to just put an example right here. Let's say we're talking about HF, All right, you have hydrofluoric acid. It's just a solution, nothing crazy like we haven't been working with. Here, if you added its conjugate base in the form of a salt, you can make a buffer system. So when I say salt, I'm talking about a solid. So here, an example is, let's say we added sodium fluoride. We just took that solid and we dissolved it in with the HF. Then you're going to have both of the F minus, the conjugate base, and HF present, both in weak equilibrium, okay? The other example is just going to be the opposite, but us talking about a weak base. So here we combine a weak base that's in a solution and its conjugate acid in the form of a salt. So here, a solid. An example, let's say we had a solution of ammonia. It's just in weak equilibrium. This would be kind of like 8.3 that we've talked about. And then let's say we added ammonium chloride, NH4Cl. Here, the chloride isn't going to do anything. All we care is about that ammonium coming in because that's our conjugate acid for the NH3. All right. The next two examples are based off titrations. So remember, titrations are going to be neutralization reactions, okay? So I'm going to put this right here, neutralization reactions, aka our acid-base reactions. So one thing I need us to know, the difference between 1, 2, and then 3, 4, 1 and 2, this is not a chemical change. Okay, you're literally just adding something that's already there. They're not going to react. 3 and 4 are going to react. This is going to be a chemical reaction. Okay. All right, so let's say we react a strong acid with a weak base so that the strong acid is limiting. So here, this is going to produce the weak conjugate acid of the weak base. So how this would look, and I'm going to write this in a net ionic equation form. So a strong acid, remember, we're going to write that as hydronium, H3O positive, AQ. So if you had a strong acid and you had a weak base, let's say ammonia, you just had those two in separate beakers. And then you decided to combine them. That ammonia is going to react with the strong acid to produce its own conjugate, which is ammonium. So here, knowing what we know about stoichiometry, if this will be my limiting reactant, you're going to have both the ammonia and ammonium present, left over, and remain. So this will be considered a buffer. So here, having that hydronium react with the ammonia while still having some ammonia left over after the reaction occurs, you'll make some ammonium. You'll have both components of the buffer because remember, it has to be a weak thing in its conjugate. This would be considered a buffer. Next, let's do the opposite. Here we'll have a strong base with a weak acid so that the strong base is limiting. This is going to produce that weak conjugate base of the weak acid. So let's write what that reaction would look like. So for strong bases, we'll write hydroxide. So our strong base plus, let's just use the HF example. So if you had hydroxide and HF in two separate containers, you added them together, they're going to react while making the strong base the limiting reactant. We'll be able to make the conjugate base F minus plus some water. So here you'll have HF and F minus remain afterwards. So here, same thing that I wrote above there, they will remain left over So this will be considered a buffer. Now, 3 and 4 are a little bit harder to work with, but we'll be looking at them here in the next couple of objectives. But 1 and 2 can happen. But mostly for this unit, we'll be looking more focused on 3 and 4, okay? Just because based off the problems they like to do with titrations. Overall message though, buffers cannot exist of strong acids or bases and their salts because the conjugate forms are extremely weak and the system is not in equilibrium. It has gone to full completion because the strong acid or strong base 100% dissociates. So if you see any strong acid remain, the solution's not a buffer. So in these previous examples, if the limiting reactant was not the hydroxide, it was the HF, and you had some of this left over, this is not a buffer anymore, okay? So yeah, overall, being able to decipher what is strong, what is weak is very important in this unit, and especially this objective.